Hi, I'm Howard and this is Howard Works. I wasn't going to start a YouTube channel. It was always something I was thinking about doing, and then my students suggested that maybe I should. I said no, and they said, but you could call it Howard Works, and I went, yeah, go on then. So this first video is going to be on a bit of physics called the potential divider. It's typically studied at about age 16, 17 in the UK as part of the electricity unit in the A-Level Physics course. I'm filming this video in early June, and my A-Level students will have done their first paper about a week ago, and this might have helped them revise for that. So sorry guys, if you're watching. They're not watching. Potential dividers. Let's take a look at this basic circuit first. This circuit contains three components: a battery, a voltage potential difference 36 volts, and two resistors: a 15 kilo ohm resistor, that's 15,000 ohms, and a 5 kilo ohm resistor. The goal of this first bit is to work out the voltage across both of those resistors. Now typically we'd use Ohm's Law, V equals IR, to work out the current through the entire circuit, knowing that the entire circuit resistance is 20 kilo ohms, and we can rearrange the equation V equals IR to I equals V over R, divide the 36 by 20,000, that'll give us the current the whole way through that circuit, and then use V equals IR again, using current we worked out multiplied by each resistor's resistance, it will give us the voltage across each of those resistors. But that's a bit long-winded. There is a much simpler way of doing this, and it all relies on ratios. If you divide the voltage across one bit of your circuit by the voltage across a different bit of your circuit, you get a fraction, and that fraction will be the same fraction as the resistance of the first bit of the circuit divided by the resistance of the second bit of the circuit. To put that into a formula, if we have two parts of the circuit, X and Y, then Vx over Vy is going to be equal to Rx over Ry. Rearrange as you need. I'm going to take my X as the 15 kilo ohm resistor, and I'm going to take my Y as the entire circuit. There's a reason for that. We know the voltage in the entire circuit, that's the 36 volts the battery provides. We also know the resistance of the entire circuit, that's 15 kilo ohms plus 5 kilo ohms, 20 kilo ohms. We want to work out Vx, we want to work out the voltage across that 15 kilo ohm resistor. Now, if I look at the ratio Rx over Ry, 15 kilo ohms over 20 kilo ohms, that gives me a ratio of 3/4. So the voltage across the 15 kilo ohm resistor is going to be 3/4 of the entire voltage, 36 volts, or whatever that is, 27 volts. In other words, the ratio that is the resistance of one resistor compared to the resistance of the entire circuit is the same ratio as the voltage across that resistor compared to the voltage in the entire circuit. That 15 kilo ohm resistor has 3/4 of a total circuit resistance. It also has 27 volts, 3/4 of the total circuit voltage as well. And it works both ways. For the other 5 kilo ohm resistor, we can say that that 5 kilo ohm resistor has 1/4 of the total circuit resistance, 5 kilo ohms out of the 20 kilo ohms, and it's also going to have the leftover 9 volts, the last quarter. Because it has 1/4 of the resistance, it's going to have 1/4 of the voltage as well. But it doesn't end there. If you know the voltage of one resistor, you can also use the same rule, but this time set your X to be one resistor and your Y to be the other. So you can see here that the resistances are split in a 3:1 ratio. There's 15 kilo ohms in one resistor and 5 kilo ohms in the other. One has a resistance 3 times bigger than the other one. That means it's also going to have a voltage 3 times bigger as well. If we have 36 volts, it's going to be split in that same 3:1 ratio, or 27 to 9. 27 volts going to the 15 kilo ohm resistor, and there are only 9 volts going to the 5 kilo ohm resistor. But how is this useful? It's useful because if we change one resistor out for a variable resistor, one that we manually control, we can manually change those ratios. Let's have a look. Our second circuit is the same circuit. I've just replaced the 5 kilo ohm resistor with a variable resistor now set to a lower resistance of 3 kilo ohms. The circuit's total resistance is 18 kilo ohms, and there's now a 5/6 to 1/6 split, or a 5:1 ratio split across the resistors. That means the 36 volts are going to be split in exactly the same 5:1 ratio. We have 30 volts, 5/6 of the 36 going to the 15 kilo ohm resistor, and the other 6 volts now going to the variable resistor because that's the last 6th. However, if we now change the resistance of that variable resistor up to a higher resistance, say 15 kilo ohms, that matches the 15 kilo ohms in the other resistor. The ratio is now half and half. The 36 volts is going to be split evenly between the two resistors because they've both got half the total resistance of the circuit. They're both going to get half the total voltage of the circuit as well. That is half of 36, which is 18. By the way, for some reason, exam boards love rotating their circuits by 90 degrees. If you see a circuit with a power supply at the top and then components underneath it, it's going to be a normal question about any other bit of electricity. But if you see a circuit like this one with a power supply on one side and components down the other side, it's going to be on potential dividers. I don't know why they do that, they just do. Okay, next set of circuits. Let's now swap the other resistor out with a thermistor for a temperature sensing circuit. Let's turn the variable resistor down and put the circuit in a cold environment. A cold environment means a higher resistance. We're going to assume this is an NTC thermistor. So as it gets colder, the resistance goes up, and vice versa. This one's got a resistance of 10 kilo ohms in a cold environment, and the variable resistor has been set to 2 kilo ohms, or a low resistance. That gives us a total circuit resistance of 12 kilo ohms, split in a 5-to-1 ratio. That means the voltage will also be split in a 5-to-1 ratio. 30 volts to the thermistor and the remaining 6 volts to the variable resistor. Now if we put the circuit in a hotter environment, that ratio will change. In a hotter environment, the resistance of the thermistor is going to go down. Let's say it's 4 kilo ohms like in this circuit here. Now the total circuit resistance is 6 kilo ohms split in a 2-to-1 ratio. 4 kilo ohms to 2 kilo ohms. The 36 volts is going to be split in the same 2-to-1 ratio. 24 volts now to the thermistor and 12 to the variable resistor. You can see that by changing the temperature, we've changed that ratio. This circuit can sense temperature differences. But why a variable resistor in this circuit rather than just a normal resistor? Well, having a variable resistor allows us to manually change the sensitivity of the circuit. Let's have a look at how that works. Let's put it back in the cold environment, but this time turn the resistance of the variable resistor up to 5 kilo ohms. Now in the cold environment, the resistance of the thermistor was 10 kilo ohms. So now we have 10 kilo ohms in the thermistor and we have 5 kilo ohms in our variable resistor. It's now split in the same 2-to-1 ratio as it was a minute ago, but we've achieved that at the cold temperature. And let's see what happens if we turn up the heat on the higher resistance. Now we have 4 kilo ohms in our thermistor, but we have 5 kilo ohms in our higher set variable resistor. So you've got a 4-to-5 ratio, or a 4/9 and a 5/9 split. 1/9 of 36 volts is going to be 4 volts, so you're going to have 16 volts going to the thermistor and the remaining 20 volts going to the variable resistor this time. Let's do one last circuit. It is a weird one, but I saw it in an A-Level practice paper 2 weeks ago. Let's replace one of the resistors with a voltmeter. Now, you've been told for years to never put voltmeters in series in a circuit, and there's a reason for that. They go in parallel to measure the voltage across the component they're in parallel with. If you put a voltmeter in series, it will stop your circuit from working. But here's why. Voltmeters are assumed to have infinite resistance. They don't really, it's just extremely high. So let's put a voltmeter in this circuit in series with another resistor, and let's give it a resistance of say 1 mega ohm, 1 million ohms, 1,000 times greater than the kilo ohm resistor it's in series with. So now we've got a 1 mega ohm voltmeter in series with a 1 kilo ohm resistor. The ratio of resistances in this circuit is now 1,000 to 1. The 36 volts is going to be split in the same 1,000 to 1 ratio, which means that basically all 36 volts are going to be in that voltmeter, and basically nothing is going to be in the other resistor. The current in this circuit is also going to be extremely low. That's why the circuit won't work. I hope you've enjoyed this video. Please leave a like if you have. Please subscribe if you want to see more content like this. Thanks for watching. I'm Howard, and that's how it works. But if we know how long have I got? Okay, that's good. Yeah. I shouldn't have moved that, should I? That should stay where it was. That's going to cause continuity errors. Is it blue enough? Thanks for watching. I'm Howard, and that's how it works. I got up far too early for that.